This is a new type of reaction we are going to learn now, and these are called free radical reactions. So in this presentation, we are going to learn just a few things about what radicals are and some mechanism of the reaction. So a little introduction over here, some things that we have done a little bit before, but it's been a while. So radicals are formed by homolytic cleavage. Homolytic cleavage is when you have an equal breakage of bonds, so which means that each of the atoms that is attached to the bond will take one electron from that bond. Okay, remember a bond has two electrons. So that's called homolytic cleavage. And so when you do that, you end up creating these kind of radicals. These radicals are neutral because each of them have one electron. Okay, usually when you have heterolytic cleavage, you will have one with the two electrons, one with a positive charge, right? So positive, negative, but here that's not happening. So that's important. Now, the other couple things that are important over here is number one, look at the arrow over here. This is a half-headed arrow. A half-headed arrow means that you are moving only one electron. If it was a double arrow, a double-headed arrow like we've been drawing before, that's two electrons, but this is half-headed arrow. Okay, so make sure you draw these kinds for free radical reactions. And the other thing I want to mention is right here. Okay, so the light is kind of important thing here. So either it is going to be light or some sort of energy. Okay, you need some sort of energy in order to break the bond. Otherwise, how do you break a bond? If it was that easy, then things would be just fine, or nothing would be fine, I should say. Okay, so that energy, how much energy is required depends, of course, on the bond energy. Okay, so weaker bonds, of course, will require less energy. So HF bond is very strong. That requires a lot more energy. HCl bond is easier. Now, how do you know these things? Well, there is a whole table for bond energies that you can look at. Okay, but we will not be calculating a lot of all of this, but it's good to know which bonds are going to break and which are not, because then you can write your reactions properly. Okay, so I'll just go over that when the time comes. The radicals that are formed are usually going to be high in energy, and so they are very reactive. Okay, radical reactions are very different from the substitutions and eliminations that we've been doing, because the positive and negative leads to weaker acids, weaker bases, right? That's the whole point of reactions. But in radical reactions, they're very different, and these reactions can keep going on and on. Okay, so we'll talk about that also. Free radical reactions mechanisms is also going to be very different than what we have been doing. There is no electrophile, there is no nucleophile. There are three steps that we're going to talk about: initiation, propagation, termination, as we learn about the mechanisms. Just to go over a little bit about the stability of radicals, it is just like the carbocations, okay, which means that the primary is going to be, or the methyl radical is the least stable, then primary, secondary, tertiary, and then the resonance one, that is the most stable radical, okay, of all. I have shown you here how the resonance of the double bond works, okay, for radicals. So you'll see all here, this is half-headed arrows. And so in the double bond, one electron is coming on this side, one electron is going on there. This one electron is moving over here, so it gives you the double bond, okay, on this side now. So the resonance leads to a lot of stability. So the resonance radicals are going to be even more stable than the tertiary radicals, okay? But otherwise, the stability is exactly the same as carbocations. Now remember, these are called allyl radicals. Allyl would be the 1, 2, 3 kind of thing I've taught you before, okay? If you forgot, it's coming up, okay? We'll do it again. All right, so first problem here, arrange the following radicals in order of their stability. So of course, all you have to do is find which one is the least and most, depending on, of course, like here, like the double bond. Soon as you have the double bond, that might be it, but then again, you have to look for that 1, 2, 3, and that 1, 2, 3 is 1, 2, 3. Okay, so if the double bond was not the 1, 2, 3, if it was like this, then it's too far for resonance. So this is not going to be anything else but a secondary radical. Okay, this is just secondary. This is not an allyl radical. A 1, 2, 3, that's an allyl radical. So that's going to be the most stable. So what did I do over here? Okay, this is not tertiary. This is supposed to be 3. Okay, 3 is the allylic radical, so that's good. And then 2 is tertiary, and so on and so forth. Okay, so that's the kind of question you might get for stability of radicals, which is kind of a common thing. And then write all the radicals that are possible for the following compound and identify which radical will be the major product. Okay, so again, it's just about the stability, because the more stable something is, then that's the major product you get. Okay, so the first answer is just going to go ahead and draw the radicals on each. I'm not showing you how to form the radical. I'm just asking you to write the radical, okay, that you will have. So this is just a secondary. This is not really allylic in any way, so this one is not going to work out. Okay, so that's wrong there. This one is allylic, okay, because that is 1, 2, 3. Okay, that's how it's going to work. So the allylic radical, this is not allylic, remember, okay, this is just a tertiary radical. So the allylic radical is going to give you the major product. Okay, that's how it works. So sorry about this one. I'm going to cross that out later. So what kind of reactions can you do with radical reactions? Well, a lot. Okay, so here are just a few of them, most common ones. Now here I'm just taking bromine as an example, but you can have other reagents also. A lot of these reactions are determined by energetics, which means what bonds can break, and that's why you can't do all reactions with radical reactions, but there are some that radical reactions are really good with, okay, or for. Okay, so first reaction that I want to talk about is the substitution reaction. It's the example, and the substitution here is on an alkane with bromine to give an alkyl halide. Now this is a very unique kind of a reaction, okay, because first of all, we haven't done any reactions on alkanes yet, right? We've done reactions on alkyl halides, the substitution elimination. We've done some reaction on, well, a lot of reactions on alkenes and alkynes, but not on alkanes. So this reaction is really, quite unique. The other thing I want you to note here is that it's a substitution reaction, which means that you are substituting something. So here, what are you substituting? Well, you're substituting a hydrogen with bromine. So which means what? It means that the leaving group is H, and not just H, it's actually H minus. If you were doing a proper substitution reaction, right, you need a leaving group. So H minus as a leaving group is a terrible leaving group because it's a really strong conjugate base of hydrogen, and hydrogen is not even an acid, right? So the pK is very high, so which means that H minus is a terrible, terrible leaving group, which we've talked about before. So which means that this reaction is really quite unique, because here we are doing a substitution using bromine and hydrogen as a, hydride as a leaving group. But the hydride here is not as a leaving group as what we would think, right? Because we are dealing with radical reaction. So it's a completely different mechanism, which is why, this makes this reaction, a substitution reaction, a very unique kind of a reaction. But anyhow, let's move on. So here then we have allylic substitution. Allylic substitution, again, it's a substitution. Again, you're substituting a hydrogen here, and it's a allylic substitution, meaning a 1, 2, 3 substitution. So on the third carbon, you have a bromine. And the third reaction is an addition reaction, which is, an alkene, which if you remember, if you take an alkene and add HBr to that, you get a Markovnikov addition. So hydrogen should go to the carbon with more hydrogen, but here it's the opposite. So which means this is an anti-Markovnikov reaction or product. And so how does this work? And this also gives us another way of making an alkyl halide where we don't have to worry about Markovnikov products. Okay, so it just gives us more choices of what you want to make. So then the last reaction here is a coupling reaction, and coupling reaction is when you want to take two alkanes and join them together. Okay, so we've talked about carbon-carbon bond formation only once so far, which has been with an alkyne as in a chain elongation. Okay, and so this is also very unique kind of a reaction. Okay, there's only energy over here. Of course, you need other things. Okay, and I haven't put everything over here because we will do mechanisms. But anyhow, these are the 4 reactions, and we'll go through all of these except for coupling. I don't do much of number 4 a whole lot, but the first 3 we will definitely talk about more as we go on. Okay, so let's talk just a little bit about the energetics here, so you can do that later. But anyway, in all of the radical reactions, you're going to need some energy to break the bond, okay, which means you need to know what bond energies you're dealing with. So for example, over here with the HH and the Cl, so like hydrogen bond and the chlorine bond, a hydrogen bond is a lot harder to break. As you can see, a lot of energy is being given off here, which means this bond has higher energy. Then chlorine is easier to break. Okay, so this kind of helps us to decide what reagent we need to start with. So chlorine is a better reagent to do this free radical reaction with. Okay, now do you have to remember all of this? No, you don't. But you do need to remember that you cannot use hydrogen. Okay, so if you don't want to remember the numbers, that's totally fine. Usually nobody can anyway, so you have to use data tables in order to figure this out. So, but I'm going to give you, as we go on, some idea as to what kind of bonds to break, so you don't have to look at the energetics, or the bond energies for doing all the reactions. Similarly here, when you have a primary hydrogen versus a secondary hydrogen, it's much easier to break a secondary hydrogen because the secondary radical is a lot easier to form. Okay, and so therefore, this is better, okay, in a way. So which means that this is a better starting material, which, both of these are same, but, you can tell that this bond is going to break a lot easier than this one. Okay, and I'm missing a radical here, which I will add later on. Okay, let me just add one here for now. Okay, all right, so those are the bond energetics. There's a little bit more. And this slide doesn't give you a whole lot of information except that, what kind of bonds to break. And so in the next slide, I just wanted to introduce what's coming up, and that's the energetics for a lot of halogenations. So remember, you can do substitution. So, but what do you want to substitute with? Fluorine, chlorine, bromine, or iodine. And so, I've given you some examples here so you can see how the bond energy values can actually affect your reaction energetics. So here is for fluorine, chlorine, bromine, and iodine. Okay, so this is all these reactions here with the bond energies. Delta H, we've done enthalpies before. So each reaction is involved with the enthalpy of reaction. And then when you do the delta H total, this is what comes out. Okay, and so once this is happening, you can see that a lot of energy is given off over here, which means that this is very, very hard to do reaction because it's very exothermic. And so this reaction can be very explosive. Okay, so nobody wants to have that much energy reaction because then you need special conditions for that. Okay, chlorination and bromination is a lot easier to do. You can see the difference right away, right, from fluorine to chlorine also. Chlorine still is a little bit harder to work with. Bromine is a lot easier to work with. So which is why, I gave you examples of a lot of bromine because we will be using bromine a lot. Okay, and then iodine is positive, which means that actually this reaction has a very high activation energy, and you cannot, it's very hard to do this reaction. Okay, so it'll need a lot of energy. So high activation energy, and also endothermic tells you it needs a lot of energy in order to do this reaction. So iodine fluorination nobody does. Chlorine and bromine, yes, we use these a lot. Bromine a lot more than chlorine also for that matter. Okay, so as we go on, focus on these two halogens. And by the way, in case you're wondering, do we do only halogenations for free radical? And the answer is yes. Okay, so there goes another thing, which means that you don't have that many reactions to remember. It's just halogenations. Okay, so the mechanism of the reaction, as I said, this is three-step mechanism: initiation, propagation, termination. So I'll take you through the mechanism, one by one. So here's the initiation. Initiation is when you have the homolytic cleavage, you're forming radicals. Okay, to form radicals, you need some sort of energy. What sort of energy do you need? You need either light energy, which is written as h nu, because that's the Planck's equation. And Planck's equation is represented by E is equal to h nu, or you can use an heat energy. Heat energy is represented by delta, okay, this triangle symbol. So you can use either of those symbols to show that you are doing a free radical reaction. There is one other way that I'm going to tell you later on, okay, as to what you can use to show that you're doing radical reactions, because otherwise, you know, if you don't use that energy or that indication that you're doing free radical, then the products can be very different. Okay, so you have to indicate that. What does initiation do? Initiation makes you radicals, not you radicals, okay, makes the chemicals radicals. So here we have the chlorine, for example. You've seen this before. I've shown you the homolytic cleavage. So that's all that's going on here is you take chlorine, you provide light to it, it undergoes bond breakage, and you end up getting two radicals. First of all, why do you need to do initiation? You need to do initiation so you can get radicals to get the reaction started, okay? Because the bond energies that we're talking about, Cl-Cl bond is a lot easier to break than a CH bond, okay? So that's why you start your reaction with something that can easily break and form radicals. When you provide energy, the Cl is not going to form a cation or an anion. That's never going to happen, okay? You can only form radicals from this. Once the radicals are formed, then the propagation is going to happen, okay? The CH bond is never going to break to give radicals in the initiation step. Again, why? Because the energy is too high. Okay, you don't want to use up all your energy just to do the initiation. Initiation should be easy. And once you form radical, as I said before, they're very reactive, and then they can cause the breakage of these bonds then. Okay, and that's the propagation step that we're going to go to. So in case you're wondering, why don't we have any other substrate here? Is because you don't want to use too much energy. Okay, so you want bonds that can break with low energy. Another bond that can break with low energy is a peroxide bond. So peroxide, as in H2O2, hydrogen peroxide, or benzoyl peroxide, whatever peroxide it might be. Peroxide just means that you have more oxygen, and the bonding is going to look like this. So you can also show, you know, a random peroxide like this where R can be anything. Okay, so once you have this bond, the oxygen bond here is quite weak, okay, and it'll break up. And so if you were breaking this up, you would end up getting two of these radicals, okay, in there. So you end up getting two, in this case hydroxy, this is hydroxy radicals, but otherwise these would be then the alkoxy radicals. Okay, so you end up forming these radicals. By the way, here also you can use bromine, right? So as I use over here, so chlorides or bromides, I use, and I shouldn't say chlorides and bromides, actually should be chlorine and bromine. Okay, should be used, can be used as initiators. Okay. Now for the propagation, once the radical has formed, okay, the one radical that is reactive with the low energy, once that is formed, then that initiator radical will start doing the reaction. So generally what you want to do is, you know, if you're doing halogenation, then you can go ahead and use that halogen as your starting initiator also. But if you don't have that initiator, okay, as also your substrate, you know, one of your substrates or reagents, then you can use the peroxide. Okay, so if you're using peroxide as an initiator, usually the peroxide is not part of the product. That is just an initiator to help to break the CH bond. Okay, because then what happens is then once you form the methyl radical, that can do the reactions now. Okay, so I hope you understand what I'm trying to say. Okay, that, you know, you can use the peroxy radicals when this is not really part of your product. Okay, and something else you need to react. Okay, like the coupling reaction you need to do, or some other addition reactions you need to do, then you can use peroxide. You can also use bromide, but then you will use those ones in a very small quantity. Okay, if you're trying to use halogen as also part of your product, like in this case, then you need lots of halogen, okay, because you need the molar ratio in there. I hope I'm trying to convey what I'm trying to say here is that, you know, are you using that as an initiator or are you using it as a substrate, okay, and a reagent? Okay, so in this case, let's talk about propagation reaction. So propagation reaction is that once you have your radical, okay, that you need, then that radical can start reacting with your substrate. So here, let's say we are trying to make CH3Cl, methyl chloride. So here now the radical can break this CH bond. And now you do need the energy to keep the reaction going, but you don't need that much energy to break the CH bond. The radical will do that for you. Okay, so that radical now will break the CH bond to give HCl, and you create a methyl radical. Now that methyl radical can break another chlorine bond, and then you know, it can give you CH3Cl and a chlorine radical. So here, because chlorine is part of the reaction, part of the product, it means you need a lot of chlorine in there. Okay, so not all chlorine is going to be in radical form. You will have some chlorines in there. One of the things about the radical reactions that, you know, it kind of boggles the students is that, you know, can I use this radical again? Can I use this molecule again? Is this molecule present in the reaction mixture? Yes, they are all present. Okay, so not all chlorine has been converted to radicals, and you will have methyl radicals once you're at the propagation step, and you will have the chloromethane. You will still have chlorine in there. So you'll have all sorts of things, and then whatever you want to do your reaction and write your mechanism with, you can use all those species. Now, there is one key aspect about propagation that is really important, and that's that you should always have a radical as a product. Okay, so radical is going to be part of the product, and that shows you that you are doing propagation. If it's not, then you're not doing propagation. Okay. And the last step of the reaction is then the termination step. Termination tells you what you're trying to do here is that you're trying to stop the reaction from happening. Okay, so there are a few ways that you can stop the reaction from happening, and one of them is to, you know, add a quencher or a terminator, as we say. So, you know, that should just take care of it. And a terminator or a quencher, what is that? It's going to be a chemical that absorbs free radicals. Okay, now we eat you know, quenchers all the time, which is vitamin E and A, C also. Sorry, not A. Vitamin C and E, those are quenchers, and so you can add those kind of chemicals to these reactions, and then they will just gobble up all the radicals, okay, in there. So either that is one way you can do it, and there is another way to do it, which I don't think I have written over here, but I would like you to think about it, and you can email me and let me know how you can stop this reaction a second way. Or if you want, I'll answer the question. Actually, I've already answered the question before, but I'll answer the question in, you know, in a second or two once I finished explaining this. Anyhow, okay, so what's happening here? In the termination step, there should be no radicals left in the product. Okay, so what is a termination step? All the radicals will start combining to give you something that is a whole molecule, a complete molecule, non-reactive kind of a molecule. So you can react pretty much any two radicals to give you a molecule. That's it. Okay, the key thing over here in termination is that you should not have any radicals left over. You can form the product also. Okay, so here we are forming the product, but usually when I ask you for the mechanism of a reaction, I don't want you to give me just the initiation and termination by forming the product. No, I would like you to do initiation, do a propagation step, and then do a termination step. Okay, so you have to write radical mechanism always in these three steps. That's when we know that the mechanism is complete. Okay, all right, so I don't know if you thought about the other way to stop the reaction, and that is to remove the energy. Okay, and here is the entire reaction for you, okay, all on one page. So if you were to show me a mechanism for this kind of a reaction using free radicals, you would show me the initiation step, you would show me the propagation step, and then you will show me termination. And I've written all the steps here again. You can pick whichever one you want, okay? But as far as the propagation, you have to show these two. Why? Because here is your product. This one doesn't have the product in it, okay? So this has the product, so you have to show me that. Now, this is over here also, right? So you have the product here as well, but you know, um, you can show both steps if you want to, okay? One thing you can probably assess already is, you know, how many different kinds of products you can get from a free radical reaction, and that's a common problem. Okay, solve problems. So let's see, mechanism and radical reaction. So write all the products that can be formed from the radical reaction of methyl cyclopentane with chlorine. Give the mechanism for formation of the major product. Very typical kind of a question you can get for radical reactions. So the first part is forming the products, which is just actually writing all the constitutional isomers for cyclopentane, but you know, putting chlorine in different places. So here is the reaction condition. You need to show that this is a free radical reaction, okay? So if you were just to put chlorine there, it is not acceptable, okay? So you have to either have to put heat in there or light, you know, something like that to show that this is a free radical reaction. And then, so these are the products you will get. So chlorine on the methyl, chlorine over here, chlorine here, chlorine here. If you move this once more, you'll get the same thing, okay? So the major product is going to be the one that forms from the tertiary radical. So that's this one. So which means that we show the mechanism just for this product, okay? The mechanism should involve 3 steps: initiation, propagation, termination. Initiation is easy. Chlorine breaks apart to give you 2 radicals. So the first step, generally for propagation, you're going to have 2 steps, okay? One step is going to be the formation of the radical for the alkane. Once you form the radical for the alkane, then is the formation of the product. And remember, since you're showing propagation steps, you always should have radicals in the products, okay? At least one radical, either from chlorine or from the alkane, it doesn't matter, okay? So here is your product forming from the propagation step, and then I also form the product in the termination step, okay? Last thing I want to just mention here before I move on is please pay attention to the arrows, okay? These are all half-headed arrows, and you also please make sure, okay, that you draw only half-headed arrows for these mechanisms. So one of the most or biggest problem of radical reaction is the reactivity. Okay, so as I said, you know, once you get the reaction started, okay, which means that chlorine, you know, is starting the reaction initiation, then the reaction keeps happening in either of the 2 cases. Either you don't have anything to form anymore, which is very rare that it happens, or the second thing is that you run out of energy, okay? So either of those 2 things happen, otherwise these reactions keep going on and on and on and on, and these are called chain reactions then, okay? So they never finish. And so what happens is that, you know, you end up getting products that you did not really want. So for example, if you take methane, react it with chlorine, you will get methyl chloride, more chlorine dichloromethane, more chlorine chloroform, and then finally carbon tetrachloride. Once you form this, this is not going to form CH, it's not going to form chloroform back, okay? So this is it. So which means that if you're trying to form carbon tetrachloride, fantastic. But if you're trying to make chloromethane, this is going to be a very hard reaction for you to control, because you will end up getting multiple products, okay? So when you do free radical reactions, then you have to very selectively choose what you want to make, okay? So for example, in the problem we just did with the methyl cyclopentane, is you are trying to get a major product there. So even if you have other products, at least one of them is going to be major. For something like, you know, trying to make chloromethane from methane, that's not going to work, okay? Because there is no way that this is more stable than dichloromethane. So, you know, you're going to form everything in equal amounts, and then you'll have such a mess on your hands, you know. So that's one of the problems, okay, for radical reactions. So you have to be very selective in what you're trying to make. So here are some problems you can have for, dye substitution. So for example, what I showed you was taking methyl cyclopentane and making just this one product. Okay. Now you have to be very careful in monitoring this reaction. I told you, okay, write me the the mono substitution, pick out the major product from there and write the mechanism. Does it mean the reaction is behaving like that? Of course not. The reaction has a mind of its own and it's going to do whatever it can so to keep going. And this is what it does, okay, is it ends up forming so many constitutional isomers, okay, and not because it wants to or anything like that. It can't help itself. Okay, that's the reaction. There is a substrate. It's going to do mono substitutions, di substitutions. I haven't even written out the tri substitutions over here. Okay, so if you have enough energy, you have enough chlorine, then it's going to keep happening. So how can you control any of this? It's going to be very hard. Either you control the temperature or you make sure that you isolate your product and keep separating it out. Otherwise, it's just a big mess, okay, that you can get. So some reactions are just not, very good to do, okay, in these kind of situations. So that brings us to bromine, okay, because chlorine actually is a very, very reactive substance, okay. So here I've shown you the regioselectivity of bromine, all right. So here you have an alkane, just butane, and you treat it with bromine in free radical reaction and you end up getting two products, okay. Those are the two mono substitutions that you're getting. This is the major product, this is the minor. Why? Because secondary and then primary, right? So secondary halide is form more because from secondary radical. In chlorine, both of these products are going to be almost equal in quantity. Chlorine is not very selective in how it's reacting. And so in the previous slide, when I showed you all those products for methyl cyclopentane, you're going to get all those products because chlorine is not selective at all. If you were doing bromination from that reaction, then yeah, you can say you can have one product. And that was the mechanism we wrote, right? The tertiary halide. But for chlorination, it's not a good idea. So which means what? It means that if you want to have selective products, you choose bromination. Don't choose chlorine. Okay, chlorine is going to be very reactive. Now you can go back to the energetics slide if you want to. And I remember I said fluorine is highly exothermic, very high reaction, very hard to control. Chlorine was the next one, okay, and then it's, bromine, you can see requires very less energy. So bromine is a very slow radical to form, not very slow, it's a slow radical to form, and because it's a slow radical to form, it will also react slowly. So when it reacts slowly, it can be more selective in its reaction, okay? When something is fast, it's not selective at all. It's just going to react with anything, okay? So, it's a hard reaction to control at that point, all right? So here I've given you some numbers if you need, but otherwise, just remember that bromine is a little bit better to work with than chlorine. All right, the other thing I want to talk about is the stereochemistry of the products. All right, so the stereochemistry, because we haven't talked about that, we've just talked about you'll get a lot of constitutional isomers, which itself is a pain in the behind. And now we're talking about stereochemistry, which also leads to enantiomers. Okay, so here in this case, for example, when you take butane and you treat this with bromine, you form a radical. This radical is more like an sp2 hybridized carbon, which means it's trigonal planar. If it is trigonal planar, the blue and the pink shows you that the bromine can attack from either side, giving you a chiral center. Okay, so as soon as you have a chiral center, you will have enantiomers. If you have enantiomers, okay, now we need to separate them out by resolution. Okay, and so keep this in mind also. I did not even write chiral products in the previous slides, but it is possible to form, chiral products. Okay, so another issue to keep in mind. Now for the radical reactions on alkenes with bromination. So now we're just going to focus on bromine. We're not going to talk about chlorine because we know chlorine is not very selective. Okay, so which means that all of these reactions now that I'm going to talk about, just a couple more reactions to talk about, those are all for bromine and not for chlorine. Okay, so the top reaction I've given you is an addition reaction because that's what we're talking about, addition reaction. So the top reaction is a very typical addition reaction we have done for alkene, which is you take an alkene, add HBr. This is going to be Markovnikov because, and I know because we don't draw the hydrogen, sometimes it's hard to see, but you know, here is the hydrogen. So hydrogen goes to the carbon with more hydrogen. So this is a Markovnikov product that you end up getting. If you use HBr in presence of peroxides or light or energy, then you end up getting hydrogen in the other place, in the other carbon, on the other double bond. Okay, so remember, this is how it is. So now the hydrogen is going to the carbon with less hydrogen, so that is an anti-Markovnikov product. So which means that just changing the conditions of the reaction will change the kind of product you are getting, and I shouldn't do this, okay, will change the kind of product you're getting, Markovnikov versus anti-Markovnikov. So if you did not want Markovnikov product from a traditional addition of HBr, then all you have to do is a free radical reaction and you will get the anti-Markovnikov. Now remember, chlorination is not going to do this, so don't even try to do this with chlorine. Okay, this is only for bromination, and that's it. Okay, so why is this working? Why is it that it's anti-Markovnikov? And for that, you have to see the mechanism. Okay, and the mechanism is that once you add a bromine radical, the radical is going to form on the secondary carbon, not on the primary. So the primary carbon or the first carbon is the one that's going to add on the bromine in order to get a more stable radical. So then when the H comes in, it's going to add on to the more stable radical. Now the same thing was happening in the case of addition of HBr, except that we were adding hydrogen first. Here we are adding bromine first, okay, because bromine was the initiator. So bromine actually adds first, and then you add the hydrogen. Okay, so it's a little bit different mechanism, as you can see, although it is still to do with the stability of the intermediate, which in this case it was, you know, a carbocation, and in this case it's a radical. So it's still to do with the stability. Okay, so this is one reaction you have to remember then, okay, and the conditions and the fact that it's anti-Markovnikov. Now one more thing I just want to say before I move on from here is I'm trying to give you different conditions that you can write to show that something is free radical reaction. Okay, and so over here I gave you peroxides. I could have easily written heat. I could have easily written this also. Okay, and you can also do that if you want to. So you don't have to write all of them. You can just write either of them. Okay, and it will still mean that you're doing a free radical reaction. And here is another reaction, and specifically of bromine, and that is the allylic substitution. Again, no chlorine, okay, only bromination here. So allylic bromination is a very specific free radical reaction mechanism, and again, it's an allylic substitution, so which means a 1, 2, 3, the third carbon from the double bond is the one that is getting substituted with bromine. Okay, so this is kind of what the reaction looks like. Again, remember the third position from the double bond is where the reaction is happening, and again, only bromination, no chlorination. So how does this happen? Again, the conditions just, you know, bromine and light or free radical, you know, conditions. So here, once you form the free radical, the first reaction is to remove the hydrogen to form this radical. And why is this radical forming? Is because you can get resonance, okay, from here. So that's what I've shown you in this case. That's why the radical doesn't form on this carbon or this carbon or the other one. Okay, only the allylic hydrogen is removed because only that position is going to give you more stable radicals. Okay, so this reaction is actually quite good. All right, you will not get any other products in this case. So then, you know, you add on the bromine, you do end up getting two products because you're forming both of these. And by the way, this is one way of knowing that you have resonance. Okay, the fact that you're getting two products is, is a result of the fact that you have two resonance structures. So in any case, you have the two products, and but in both cases, it's bromination. Now, Br2 is the common reagent that is used over here. So remember when we did halogenation way back, when we took an alkene, and if you were to just add bromine to this, you would end up getting something like this, right? The bromine would add just like this. But in this case, because the condition is different, you're getting allylic bromination. Okay, so remember, these conditions make such a huge difference. Just like we talked about in the previous slide with the HBr, adding HBr just like that will give you Markovnikov, but HBr with free radical mechanism gives you anti-Markovnikov. So similarly here also, all your conditions are going to make a big difference, okay, in what you're trying to make. The other reagent you can use here is called N-bromosuccinimide. Yeah, I'm missing the Br over here, so I'm going to add that later on. So bromosuccinimide, N-bromosuccinimide is also for the short form NBS. This reagent you can also use, and by the way, when you write NBS, you don't have to write H nu, because it's kind of understood that you're using free radical mechanism, okay, for this, because that's the only way this reagent works. All right, so either of those two is going to work just fine in order for us to do allylic substitutions. Okay, I can see we are almost at the end because I have a last word here. But anyhow, so one word I would like you to learn also is chain reaction. Chain reaction is a word for propagation steps. I used the word chain reaction before, but chain reaction is kind of interestingly used only for free radical reactions, because once the radicals are formed, they just keep reacting, okay, and it's just going on and on and on and on. So unless, as I said, either you add a terminator, to that, or you remove the energy source, okay, so either of those two things is needed. Yeah, you need to call, Mr. Schwarzenegger for this, but anyway, jokes aside, it's really hard to control. So it's called chain reaction. And the last thing that I would like to say over here, when you're doing all of these reactions, please do not break any carbon-carbon bond. Okay, so we break only the CH bond. So if you see all the mechanisms I have done for you, you only break CH bond, no CC bond. And that CH bond is also broken only in the propagation step. Okay, not in the initiation. Initiation needs very, low energy bond breakage kind of things like peroxides and halides. Okay, so be very specific in your reactions and steps and bond breakage. And I think that's it.